Very good, thank you. Good morning, everybody. I'm the only thing, well, yes. Wait till you hear what I have to say. I've had a very, very warm welcome in Romania and a very warm weather to go with it as well, which as a British person is obviously constantly the only topic of conversation that we have. Right, today I'm going to talk about supply chain, policy, automation, and OCI, artifact signing and cryptography. And hopefully make that a contiguous narrative. So hi, I'm Andy. I'm CEO at ControlPlane. We are a cloud-native security consultancy with an FSI regulated industry specialism. That just means very good DevOps. Security is then an acceptance criteria on top, and then we have security automation and no pointing and clicking, and various other things. Open UK is a non-profit based out of the UK, where we focus on open source, open hardware, and open data. And we try and stop the UK government from just shooting its foot off with various pieces of crazy legislation. I am still a fervent open source contributor, and as well as an author and trainer, etc., etc. So, what is the supply chain? Why is it so painful? Why are we here? Then what legislation? This Cyber Resilience Act is a European Union piece of legislation which, like GDPR, impacts anybody who does business in the EU. CVE management, well, cyber resilience plays into these CVEs, we'll see what that means, and then into some flux, getting into the technical delivery aspects of keeping systems secure. Policy as code, and then a little teaser, what's the next generation of Helm going to look like? So please mind the gap, this is not the London transit system, but it's a clearer description or a clearer visualization. Cyber resilience. So it's now 2025, and we keep on seeing supply chain attacks. Why is this the case? Well, because it's quite an easy way to break in to hundreds or thousands of systems simultaneously. What might a supply chain attack look like? Well, the top one there, XZ, it's attacking a maintainer, just wearing them down, joining in and fooling them into think that you're a nice maintainer. Then all your friends come and criticize the person, you get the commit bit, and then you ship some really nasty code, which in that case gave backdoor access to SSH across the board. If you ran SSH through systemd, then you could pass special packet headers, and boom, all SSH is open. Fortunately, that was detected before it hit mass deployment, but it was public. It made it into lots of distributions. We've seen other things. Polyfill, of course, is the front-end version of that, where somebody takes control of a JavaScript library, and then they ship code that is probably not the code you want to run in your browser. Polyfill sits on loads of different websites, so suddenly you've potentially got cookie access. So the point here, these attacks can amplify their magnitude very, very easily because we all consume open source, because the contract between free, non-liable open source maintainers and the biggest organizations in the world is, thank you very much. We've just got that for free. We've got transferable value because individuals can now change jobs and take that knowledge with them, and we can debug the thing. We're not paying vendors for the closed source illusion of safety that comes with it. So we're seeing loads of supply chain attacks. They are often targeted against very large institutions as well. And there's a particularly malevolent version here. So typo squatting is where I make a library called Andy test, let's say. And then everybody installs it because it tests to see if you're Andy, and you're not. So boom, runs across everywhere, great. We're all pretty safe, we're not Andy. And then somebody uses maybe the letter S and puts it on the end, Andy tests. And when you do an npm install, or you're manually installing these packages, they've cloned the exact code to a new repo with the same name, but one changed letter. So it works. Nobody notices. And then you get 10,000 installs, you drop in a backdoor, CI merges it, and all of a sudden, everybody's running malicious code. That's typo squatting. It's got 10 times as bad with AI, because AI is hallucinating packages that people are then going and registering and dropping in. So it looks like it works, but again, the trust between the maintainer and the consumer isn't there, because that's a malicious maintainer using valid code. There are other nuanced ways of doing this with strange character sets, different spellings, localizations, but broadly, there's a lot of supply chain attacks going on, and everything's vulnerable. There's nothing that we can't add to this list, because the entire world is based upon consumer and producer supply chains, and software is a digital evocation of that same trust. So, red team, blue team, there's no such thing as secure software. Software that stands still dies, because technology advances, attacks against systems range from hardware through to users. So we have to keep on moving. We have to be innovating at the same pace of change as we do as a society, which ultimately results in chasing our tails. And because IoT often doesn't have any sort of upgrade path, you end up with this, the European Union Cyber Resilience Act, which says there are so many malicious light bulbs that they formed a botnet that you might have heard about a few years ago called Mirai, that then went and attacked places like Maersk. We're into $20 billion insurance claims when you can't transport things on ships. So the European Union says, right, we're going to try and fix open source. And the way they decided to do that was an unexpected surprise, making software producers, of which open source maintainers count as producers, liable. That is the antithesis of an open source zero liability license, as we publish everything with and have done for many years. It's been ameliorated slightly, so there's now a bit of a gray area where it's only if you are selling open source that you might be in scope. This legislation will come into force in the next year or so. Nobody knows exactly how it will be enforced or who will be liable, but suffice to say, there is now potentially a legal imperative to ship secure software as an open source maintainer. Now, that's the very worst version of this. The slightly brighter version is that actually this should increase the baseline level of security. What it does mean is that we have to be able to build, package, deploy, and run software as quickly as possible, which is a good thing from a security perspective. We know that software will eternally have vulnerabilities. Vulnerability scanning will get the right results sometimes, not always. And software bills of materials are part of the answer. So, now we know there's a problem, and that's the very worst version of the problem it could be. How do we manage that? So a CVE turns up in my application, and it's in a dependency, so it's outside of my control. What do I do? How do I make sure that I'm shipping software that is patched and secure when that patch is only a dependency version bump? So it's not the code that I wrote, it's the code that I'm consuming, but because I'm shipping it, I have that liability. So what we'll talk about here, nothing here is universal. These are broad swathe, slightly abstract, but with concrete examples. Secure practices often beat crazy advanced stuff, and if your house isn't in order and you haven't fixed Cloud IAM or Git signing, insecure SDLC, misconfiguration, static analysis, probably go and fix that first, because supply chain attacks, as I say, can be targeted and are more general, but you probably want to fix the sort of lower hanging fruit. For the rest of this as well, we'll assume you've got an SDLC defined, and a source repository and secure build system, and some package caching as well. So first of all, from a typo squatting perspective, we have to verify and validate the provenance and the veracity of the source code that we pull in, the binaries, the container base images, the configuration. Everything should be signed, and the cryptographic public key that we share with that thing validated. So we know it's coming from somebody who was in control of a key that we trusted at that point in time. That's all it means. The person who had control of the cryptography liked this thing enough to put a stamp on it. They may have been compromised themselves, but that's better than potentially a middleman attack or, again, a typo squatting style. There's lots of ways of signing things now. Sigstore has now got wide public infrastructure for distributing key material and signatures. And this concept of SALSA, the software supply chain attestations, essentially, basically says you're better off just signing everything that you've got and storing it somewhere than you are doing nothing, because then you have a data lake. You have some form of forensics, some form of analysis that you can do after the event of compromise. And going full circle, as a software product, Flux will do a lot of these things for you. When Flux is building itself, it generates a software bill of materials. That is a recipe to say, these are the things that I've cooked myself out of. And that's important, because if one of those has a vulnerability, we want to be able to query all the installations of that vulnerable package without having to get a magnifying glass or SSH into everything or do scans of container images in production. So we generate a bill of materials, we sign it, and we store it, because it's just data that we can use offline to validate what we've got deployed online. These signed SALSA attestations are little cryptographic tokens. It's a little bit of JSON, and you create a hash, and you sign that hash to say the person who held this cryptographic key liked this thing enough to sign it, and you've got a little bit more trust that theoretically can't be broken in modern cryptographic terms. Signed images do the same thing for the image hash. So again, we're using sort of one-way cryptography to generate a sum of the software package or the configuration, and then we sign a second piece of data about that hash. So we link those two things together. It's very simple, but it's the cryptography that we're trusting there, both of the one-way hashing and then the decryptable signature. And then finally, VEX documents. If somebody finds a CVE in Flux, and they say, right, Flux is consuming this Helm library. Helm then has a dependency over here on OpenSSL, let's say. And then someone says, right, so Flux has a vulnerability. And we go and we look, and we say, OpenSSL is using a cryptographic library from 20 years ago. Flux turns that off, so that vulnerability is not relevant to me. That's not a CVE for Flux. Before VEX existed, there was no way of identifying that. What VEX does is it says, I have gone and tested the code path, and Flux can't reach that piece of code. We don't use that 20-year-old cryptography library. And so we issue a VEX document, and then the scanners stay green. So it's about getting a lot more insight, but also the ability to push back. And then when things are being deployed, Flux can validate these things through signatures at deployment time, and then we've got a chain of trust between all the artifacts back into the data lake. These SBOMs, the US government started trying to enforce mandatory creation, storage, distribution. It's half of a fix. This is also just software composition analysis. It's just scanning, you save the results, and you send them. So if I've broken into somebody else's CI, I can mess with whatever I want, change the SBOM, and then ship some broken stuff or some compromised stuff. So SBOMs are useful, but they don't just fix everything magically. And of course, they need signing, storing, and used with VEX. Otherwise, you just end up in CVE hell, where you get low-score CVEs for hundreds of packages, which you're not using in the way the vulnerability is exploitable. So we've got this concept. We're generating signatures all over the place. We're storing configuration data. We're storing build artifacts and metadata. What do we do with this? Well, it goes into a data lake, and there's some tooling emerging. In this case, this is Guac from a company called Kasari. This basically runs GraphQL over a data lake. So what happens? We've got a CVE. We query Guac to see where it's installed, and then we know where we have to make sure we fix that CVE to stay compliant, maybe from the CRA perspective, maybe we just care about secure systems, and there's other ways of doing this, as you can see with DuckDB and JQ. So, whereabouts are we in the talk? Lots of CI/CD stuff. So, we're assuming here that with this hardened CI/CD pattern, we're pulling all this supply chain metadata, these VEX documents, SBOMs, attestations, the vulnerability scan outputs for the software that we're building. We're storing everything, we're analyzing those things as they go through, and we're still doing everything that we'd normally do in a pipeline. Software composition analysis, static and dynamic testing. None of those things change. We're just adding more insights and data collection. So, can we do this in an automated way? We can, actually. So, first of all, zero-day announcement. Like I just said, vulnerability in a dependency, or potentially in a package that we're using, in a library like OpenSSL, in a container base image, in a configuration format. If somebody has switched to Boolean, which turns encryption on and off, well, potentially that is then a 0-day in a configuration file that is still going to put you out of compliance and vulnerable to CRA legislation. We then perform asset discovery. We have an inventory of all the data, of all the packages that we've installed across our, Kubernetes system is more easy because this is obviously all cloud-native tooling, but you can do this for VMs. You then automatically, for each of those vulnerable versions, do a dependabot style, bumping those package dependencies to a version that is safe. Now, there's a question here about whether we're pinning dependencies or we're relying on semantic versioning. Certainly for GitHub Actions, as we've seen, we should probably be pinning everything because there was a huge attack recently where one was compromised, cleared all the tags, added malicious code, and then repointed all of the tags at the new head. Dependabot then releases and issues all of those pull request bumps across GitHub, and speculative pull request CI then builds that vulnerable code. And that leaks the secrets that are in the build to whoever is then sniffing your environment variables. So pin risky dependencies, be conscious about your risk tolerance. What is the classification of the data you're working with? Is this pure open source? What about the consumers of your software? There's no one size fits all. But in this case, if we assume that we're running within trusted infrastructure with teams that we trust, once that pull request comes in, Flux can then see that pull request, build an ephemeral test environment, deploy that into Kubernetes, spin up the newly built software, run the end-to-end tests, the integration tests, as well as all the CI software composition analysis, and ping the user and say, hey, we had a CVE, we've now speculatively patched and tested it, all you need to do is merge it. Or, of course, because we are in the age of AI, let's do it with an AI agent. So I won't do this. Stefan did an excellent workshop yesterday if you want to see how this works at a low level. The Flux operator is a side project to Flux CD itself that deals with lifecycle management. It deals with one-shot deployment. It's got a load of quality of life enhancements for operators. And amongst other things, it now has an MCP server. This is a Model Context Protocol API shim. So it's a lot like an API, except it makes it consumable by an automated process, by an LLM. And you can see here as well, Flux also now ships resource sets, which are another quality of life enhancement, a little bit akin to what Argo does, but done in a Kubernetes native way, and it reduces the amount of YAML that you have to write. So, what are we looking at here? That AI would then not only be able to run through the pull request, there's now GitHub Copilot on pull request as well that you can just click through and get it to review the code. This AI is using Flux MCP to review the side effects and behaviors of that code at runtime, to the extent that it can through the Kubernetes API server. Okay, so now we've got the problem, we've got some CI build flows that we can do. What else can we do? Well, Flux now supports GitOps without Git. So why is this important? Well, first of all, if you have a Git server with a network route to production, Somebody who compromises production could then potentially pivot into your source code. Nice, juicy target. Second of all, most Git repositories are not production-grade software. You can DOS a Git repo or a Git-hosted service internally reasonably easily. Third of all, the security that we have around signing for Git is GPG. And GPG, as much as it has qualities, is also an old technology. GitHub is the biggest public key server in the world, which is wildness. That's the only level we have. Revocation of GPG signatures is reasonably unsolved. You have to go and query on the public key servers which keys have been revoked. In GitHub, if someone gets into your account, they can just put a different key in. Of course, that's a different compromise model, but nevertheless, the point around Git security is it's not as good as what we have for OCI. With OCI, we have SigStore, we have everything hashed as a Merkle tree, which of course it is the same in Git, but that basis gives us the ability to sign, distribute, scan, store in OCI artifacts, registries that are definitely production ready because all our containers are pulled from them. And it means that we're using the same packaging and distribution format for applications, code, policy, security in the abstract. Everything is then codified, distributed with the same security validations around it, and that gives us, again, this forensic chain of trust that we can go backwards through if something goes wrong. So we can use Cosign, which is the SigStore-based signing infrastructure. This has now been rolled out into many open source package repositories, as well as the container repositories. That's signed with Helm and Flux, and then we can verify the integrity of the Helm chart stored as OCI artifacts with Cosign before reconciling them with Flux. So somebody is able to push malicious updates unless they've signed it, unless they have the keys of the maintainer, which is essentially a secondary control. It's not going to get deployed by Flux, because Flux will check, do I know this person? Is it from a place that I trust? If the answer is no to any of the checks, it just doesn't get deployed. So we have built out an architecture to prove this. It's open source. We released it at KubeCon a couple of weeks ago. It is the D2 Git-less GitOps. D stands for design in this case. And everything is OCI all the way through. There is centralized policy, enforcement, supply chain validation. It makes life significantly easier. It also means that everything is in one place. So you can remove that network route. You can run essentially an offline first cluster with local image resolution and put all of your configuration, which again, that binary on encryption on or off, configuration is part of the supply chain, which I think is the next slide. No, we'll get there. So what does the D2 architecture do? These are features that are released into the operator as well. We have those network routes gone from production. That is a big check to enterprise architecture security teams. We have uniform signing for images and configuration. There's new multi-tenancy lockdown features, which mean you can deploy something and enforce isolation. Kubernetes doesn't have hard multi-tenancy, so another layer of reinforcement. All sorts of different scaling options, hub and spoke, sharded combination. You can do that with a one-shot multi-cluster bootstrap now. Workload identity integration across clouds, so you can use an identity provider from a different location. SOPs decryption, OCI keyless verification, and a lot more. And it's always very impressive to see how quickly the team ship these features, because I often can't keep up with exactly what's been shipped. So I use the cheat sheets. There's loads of information. The documentation is incredible. And here is a view on going from staging. We have these new Flux operator primitives called resource sets, which you can see down there on the left-hand side. And a resource set just makes it easier to deploy lots of similar-looking YAML. So at this point, we now have uniformity. We now have the ability to enforce policy as code. There is the slide I was looking for. Configuration is part of the supply chain, and that's because the largest source of cloud vulnerability is misconfiguration. Obviously, because cloud providers spend hundreds of millions or billions in building and securing infrastructure for us. It is a shared responsibility model. They do their part, give us configuration surfaces, and then we ham-fist and fat finger and end up making our own software insecure. Our own systems insecure. So, Kubernetes has now shipped Cell, the common expression language. This is a new way of writing policy, essentially. It's not that new, but it's something from inside Google. This gives us a way of writing admission controllers that can validate whatever we want. And a nice simple one is, would we want to allow an image from anywhere but our own repository? So all of our images, let's pull them in externally, scan them, validate them, sign them, push them to our internal registry, and then the only place that we can pull from is andy.controlplane.io, for example. FluxCD now integrates this, and here you can see it's used for a health check expression. This dramatically simplifies the amount of inline procedural code that we have to write, and again, just brings everything into the paradigm of Kubernetes. Things are statically defined. We're testing against a declarative set of configurations, and we're minimizing things that causes problems in distributed systems. We just let the system do it for us. There are all sorts of extra things in here. We've got validating policy for admission. I think there's actually an example at the bottom of this with, there we go, restricting access to cluster registers. And as I say, plenty more good stuff. And for the grand finale, for those of us who have been using Helm for many years, it is a little bit like Stockholm Syndrome. I had that with Jenkins, so many clusters and so many systems configured, and you kind of learn to love what you also slightly hate. Stefan has shipped Timony a couple of years ago. This uses Qlang, which is another language built out of Google that has internal self-referential validation. So it's like a database table, and the cells have formulae in to ensure that they're validated. So it's a self-testing language. This means we can replace Helm with something that is deterministic, that is only going to generate exactly what we expect afterwards, because with Helm, we can put all sorts of external inputs in that may result in two people running the same chart at different times, having different outputs. With Timony, this is all fixed. It's gaining adoption. It's still very much a alpha, beta-ish level project, but please do have a look at it. It's something that Flux is keen to integrate at the right moment in time. And with that, thank you very much for your attention. Have a wonderful day. I've been Andy.